So we start off with a couple definitions. So given a function y, given a function y of x, we define the average rates of change okay, so average rate of change, that will be delta y over delta x. Okay, so on some interval, let's say AB, we can define the average rate of change as just the change in y over the change in x for that interval. So you've all seen that before with the average gradient of the function. Okay. And we define the instantaneous rates of change of y. So instantaneous rates of change, let's say at x equals a, as dy by dx, so the derivative at the point, and we write this with a vertical line x equals a, but this just means the normal derivative evaluated at a. So if you've got some expression with the vertical line and then x equals something at the bottom, it means take whatever that is and then substitute that bottom part. So here we have the derivative evaluated at a, so we have y prime, and then inside we just put a. Okay, so that is the instantaneous rate of change. Yeah, and that's the basic idea of rates of change. You've got some function, let's say y of x, and we're looking at how this function changes. So we can look at the average change between 2 points, or we can look at the instantaneous change at a single point. Okay, the rest is just applications of this. So for our purposes, we'll mainly focus on the physics and engineering applications, but there's applications to everything. So economics, biology, chemistry. We'll look at a few examples, but mainly the physics and engineering applications. Okay, so applications in physics and engineering. Okay, so mainly these, but we'll look at some other examples as well. So firstly, in physics, we have a position. So a position of something we call x. Then we have something called speed. That is the rate of change of position. You all know that. Rate of change of position. Call that the speed. And we can write that as dx by dt. Or a different notation, if you're doing the time derivative, you can write this as x with a dot on top. Okay, then we have the acceleration. That is the rate of change of speed. Okay, everything is rates of change of something. So that's going to be a, that will be ds by dt, the rate of change of the speed. Or we could write this as d2x dt squared, the second derivative, because the speed is already the first derivative. Acceleration, that's another derivative. So the second derivative of position. Or you can write this as x with 2 dots, because there's 2 time derivatives. Okay, that's one of the applications we'll look at. Number 2, power. Okay, this is the rate of change of energy. So the power P we can write as dE by dt. Okay, rate of change of energy, that's the power. 3, mass density. Okay, so if you have some objects where the mass is not uniform, so on one part of the object is heavier, another part might be lighter. As you go through the object, there's different masses that you can measure. For example, if we got some sort of cylinder like this, then the mass can differ from left to right. It can be heavy on one side, light on the other side. So as you go from left to right, the rate of change of mass with respect to the length, that's going to change. And we give that the symbol rho. So this will be dm by dv. So v, that's the volume. So the rate of change of mass with respect to volume, we call that the mass density. Okay, number 4, electric current. Okay, so if you have an amount of charge that's moving, we define the current as dq by dt, or the rate of change of charge. So I, that will be dq by dt, right? Rate of change of charge. It's always rate of change of something. Okay, number 5, isothermal compressibility. We'll see an example with this in a bit. Okay, so later on in physics, you're going to do a whole course on thermodynamics. You'll see this quite a lot. Okay, engine cycles, compressibility, thermal expansion, Carnot cycles, all of that. So that is given by beta, and this is going to be minus 1 over v dv by dp, where p is pressure, v is volume. So it's the rate of change of volume with respect to pressure. Okay, we define that as the isothermal compressibility. Okay, you'll see a lot of that later on in physics under the course on thermodynamics. Okay, and number 6, last example, forces and potentials. Okay, so given some potential u, we can define the force F as minus the rate of change of the potential with respect to x. So just as a little example for that last one, let's say we have some potential looking like this. Then at every point, we can look at the rate of change of the potential. So let's say you start over here. Okay, and you're walking that way. As you're walking from left to right, you can see, okay, the potential is this value. You walk a bit, it changes with respect to x. And then from that, you can determine the force. So at this point here, the rate of change of the potential u is going to be negative because it's sloping down, but there's a minus sign in front. Okay, don't forget that there. So the rates of change of the potential is negative. It's decreasing, but you got a minus in front, so that gives you a positive value. So at this point, the force will be positive. It will push you that way. Okay, because this is sloping down. Then you can look at this point over here. If you're standing at that point, you can look at the rate of change. So over there, the function's going up. Okay, so it's increasing, but you got the minus sign in front of it. So that means the force at this point will be negative. Okay, so as you're going from left to right, you'll see that the force is going in the positive direction when the potential slopes down. And then when you're on that right-hand side there, the potential now slopes up, so the force is negative. Okay, so just a couple of examples with rates of change. Okay, so these are the applications. We'll have a look at a few of them as we go through. And of course, this is just the physics and engineering applications. We'll look at other ones, population growth, economics, chemistry, biology. There's plenty of rates of change problems. Okay, but again, we'll focus on the physics and engineering problems. Okay, so example 1. Okay, the position of a particle is given by, and then we have x of t is equal to t cubed minus 6t squared plus 9t. Okay, so that's the position, and there's a number of things that we want to look at. So the first thing is to find the speed. So A, find the speed. Now, I'm not going to tell you what the speed is. You know, speed is rate of change of position. So we've got the position, we want the speed. So we want d by dt of that whole right-hand side there. So the speed, let's say s for speed, that is the rate of change of position. So we know we want dx by dt. So that's going to be 3t squared minus 12t plus 9. Okay, so that's the speed. You give me a time, I can tell you what the speed of the particle is. Okay, B, when is the particle at rest? Okay, now at rest, that's a physics term. What is that in terms of maths? Well, at rest means you're not moving. Not moving means your speed is 0. So at rest means that the speed s of t is 0. So what we want to solve is, where's the speed 0? So we're going to have 3t squared minus 12t plus 9 is equal to 0. Okay, you can do your factoring and solve that. But what's really going to help, especially for the later questions, is if we plot this. So it's a parabola. We know how to plot those. So it's going to look something like this. Okay. And then when you factor it, you'll see what the x-intercepts are. We're going to have 1 over there and 3. Okay, so t equals 1, that's one of the intercepts. When you do the factoring, t equals 3, that will be the other intercept. So that's t, and this is the speed as a function of time. Okay, so you don't need to draw the whole picture just to find where the particle is at rest. But for the following questions, we're going to need this. Okay, so where's the particle at rest? Well, that's where the speed is 0. That's going to be over there and over there, the intercepts. So at t equals 1, the speed is 0, so it's at rest. At t equals 3, the speed is 0, so it's at rest. So we have t equals 1 and t equals 3. Okay, now the following question. When is the particle moving forward? And that's where the graph helps us now. So C, when is the particle moving forward? Okay, so forward means your speed is positive because you're going in the positive x direction. If your speed was negative, that just means you're going backwards. But we want to know where we're going forwards, so that means the speed must be positive. Okay, that's when we're going forwards. If the question says, when is the particle moving backwards? Well, that just means your speed is negative, and then you're going in the other direction. So let's go back to the picture. Again, this is the graph of speed versus time. We can see from 0 to 1, the graph is above the axis, so that means it's positive. From 1 to 3, the graph is below the axis, so it's negative. And then from 3 onwards, the graph is above the axis, so it's positive. And remember, this is the speed graph. So from 0 to 1, you have positive speed. From 1 to 3, you have negative speed. And from 3 onwards, you have positive speed. What we want is the positive speed. So we just read it off. So that will be from 0 to 1, and then 3 onwards. Yeah, so that's when it's moving forward. And it's moving backwards in that middle bit where the speed is negative. Okay, D, find the total distance covered in 5 seconds. So I'll set this up and then you can fill in the details for homework. So we look at the picture here. From 0 to 1, there's positive speed. So we say the particle's moving to the right. So let's say it starts over here. It's going to move to the right from t equals 0 to t equals 1. Okay, it's moving to the right. It has that positive speed. Let's say that distance is a. Then from 1 to 3, it has negative speed, so it's moving the other way. Okay, so from t equals 1 to t equals 3, it's going the other way. So let's say it's over here, and it's going to move the other way. So this is from t equals 1 to t equals 3. Let's call that distance b. So from t equals 1 to t equals 3, it turns around, goes back the other way. It covers some distance b. And then again, from the graph here, from t equals 3 onwards, the speed is now positive, so it's going back in the positive direction. So from here to t equals 5, it's moving again to the right with the positive speed. Let's call that distance c. Okay, so from t equals 0 to t equals 1, it travels a meters to the right. From t equals 1 to t equals 3, b meters to the left. And then from t equals 3 to t equals 5, c meters to the right again. So if it's going a to the right, b to the left, c back to the right, the total distance is just the sum of them. So the total distance is just the a plus b plus c. Okay, so please fill in what a, b, and c are. So that is for homework. Okay, and you've got the distance function over here. So x of t. So you're just checking what the a, b, and c are using that position function. Okay, E, find the acceleration. Okay, so let's start off with the position again. So we have, yes. How we get that? Okay, so let's go back to the speed graph here. So from t equals 0, that's over here, to t equals 1, you agree the speed is positive. So the particle's moving to the right. Okay, so from t equals 0 to t equals 1, the particle is going to move a meters to the right. And then at t equals 1, the speed is 0. So it stops. So it moves. Okay, well, come. You're going to be my particle. Yeah, come up here. Give you some bonus points for being the particle. Okay. Yeah. No, I won't. No bonus points for that. Okay. So t equals 0, you're over here. So from t equals 0 to t equals 1, the particle over here is going to have positive speed. They're going to move to the right. So
Who's my right?
they're right.
Oh,
Because they're looking. So 1 second. Okay, you've covered this distance. Okay, good. From t equals 1 to t equals 3, you agree the speed is negative. So now you're moving to the left. Okay, so this distance, now you're moving to the left.
okay.
There, left, yeah. Okay, so you traveled, yeah, just count once. Okay, now you're over here. So from there to there, that is distance, b. And now you stopped, right? At t equals 3, you stopped.
Mm-hmm.
Then from 3 to 5, you agree you have positive speed.
Mm-hmm.
So now you're moving to the right again. There, right. Okay, so go from 3 to 5. Okay, 2 seconds. Okay, that distance is c. So what's the total distance? A that you did first, plus B that you did second, and then from here to there you did C, which was third. You just add it up.
Okay.
Everyone understand? Okay, thank you, particle. Okay. Okay, so now we want to find the acceleration. So we know x of t. This is going to be t cubed minus 6t squared plus 9 times t. Okay, so we start with that. We want the acceleration, so let's do the first derivative to find the speed. So that's going to be 3t squared minus 12t plus 9. Okay, so that's the speed. Now the acceleration, that is the second derivative of position or the first derivative of the speed. Same thing. So let's do the derivative again and get the acceleration. So that will be 6t minus 12. Okay. And then the units, let's fill that in. So position, that will be in meters. The speed is dx by dt. X was in meters, T is in seconds, so this will be M at the top, S at the bottom, meters per second. And then acceleration, that was d2x by dt squared, so t squared at the bottom. So M at the top, S squared at the bottom, because we did another derivative. So it's another seconds. Okay, so that's just putting in the units, right? You know that from physics. Okay, so we got the acceleration, and then F. When is the particle speeding up or slowing down? So when is the particle speeding up / slowing down? Okay, speeding up means increase in your speed. And you can only increase your speed if you have positive acceleration, so a must be greater than 0. Slowing down means your speed is decreasing, so a must be negative to slow you down. Yeah. Or you can think of it like friction, so slowing down, a is negative, it takes away from your speed. If a is positive in that direction, it will add to your speed. Okay, so we can draw a graph for this as well. So here we have t, here we have a of t. Okay, it's just a straight line. You can sketch this quite easily, just something like that. Okay, that first little bit there, the acceleration will be negative. So this is t equals 2. So that's a minus, and then that's a plus. So from 0 to 2, a is less than 0, so negative acceleration, so slowing down. And then after t equals 2, a is positive, so you're speeding up. So negative acceleration, slowing down. And here we have positive acceleration, so speeding up. Okay. Any questions on this first example? Okay. You should all be familiar with that from physics. Okay, example 2, something from chemistry. Who's doing chemical engineering? No one. Okay. That's fine. We can just take this as an example. So given the chemical reaction, okay, so we've got A plus B makes C, whatever that is. So chemical engineering, I know you're mixing stuff to get other stuff. Okay. What we're interested in is the rate of change of the stuff that we're making. So in industry, right, you don't want to spend a lot of money with your chemical reactions. So say you're making petrol from crude oil or something, you want that to go as fast as possible. So let's say A and B is whatever you put in the reaction, C is the petrol you're getting out. If you're a chemical engineer, your boss is going to say, make the rates of change of C as large as possible. Okay, you get as much petrol per time, so you can make more money. So this is some of the equations you're going to be looking at, right, as a chemical engineer. So the initial concentrations of A and B are given by the following. Concentrations of A and B are, you use the square brackets. That just means concentration, right? Moles per liter, you know all of that. Okay, if you forgot that, doesn't matter. This is maths. So we have the concentration of A, concentration of B. That's what's going into the reaction. And what's coming out is the concentration of C. And that's going to be a function of time. And the concentration of C is given by, again, the square brackets. That just means concentration as a function of time and some alpha, some parameter. Okay, so as time goes on, the concentration will change. And we've got this equation for the concentration of C. So C is given by alpha squared T over alpha T plus 1. Okay. Right, that depends on whatever the chemical is. You end up with this equation. Okay, show that if the concentration of C is given by the variable x, then dx by dt is given by alpha minus x squared. Okay, so again, x, that's just the concentration of the product that's being produced. We want to show that the rate of change of the product being produced is equal to alpha minus the concentration of the product squared. Okay, so if you're doing chemical engineering, you're going to have a lot of these equations. Okay, so some stuff goes in, some stuff goes out. What is the rate of change of those ingredients or products? Okay, so let's start by looking at the left and the right side. Okay, so left-hand side. Right, whenever you want to prove an equation, left-hand side equals right-hand side. That's what we're trying to do. So left-hand side, that's going to be dx by dt. So that's going to be d by dt of x, but x, that's the concentration there. So that's d by dt of alpha squared t over alpha t plus 1. Okay, we've got a quotient, so we're going to have to use the quotient rule. So this is going to end up being alpha squared, alpha t plus 1 minus alpha cubed t over all of the bottom squared. Okay, hope you haven't forgotten the quotient rule. Okay, we can simplify this a bit. So the top alpha squared, we can distribute inside. So alpha cubed t plus alpha squared minus alpha cubed t all over alpha t plus 1 squared. Now the first and the last term, they're going to cancel. So we're left with alpha squared over alpha t plus 1 squared. Okay, that's about as simple as we're going to get for that left-hand side. Let's look at the right-hand side and see if they match up. So the right-hand side, that was given by this alpha minus x all squared. Okay, so let's substitute x. We know what that is. So this is going to be alpha minus the x, or the concentration. So that was alpha squared t over alpha t plus 1. Okay, so we've got these two fractions we want to put together. They have different denominators, so let's fix that. So this is going to be alpha times alpha t plus 1 over alpha t plus 1 minus alpha squared t over alpha t plus 1. Okay, same denominators. Now we can put the fractions together. So this is going to be alpha squared t plus alpha, squared. Okay, plus the alpha minus alpha squared t from that second fraction all over alpha t plus 1 squared. Okay, top and bottom squared. Now on the top, we've got alpha squared t minus alpha squared t. That can go. So we're left with alpha at the top in the brackets squared. So that's alpha squared over alpha t plus 1 squared. And we just compare that to what we had before. So that was the left-hand side. That's the right-hand side. Right, they're equal. Done. Okay, so we've matched left-hand side to right-hand side, so the equation is true. Any questions on this one? Yep. So, what was the question? Show that. So we're given the concentration of C. We want to show that the rate of change of the concentration of C is alpha minus the concentration of C squared. Prove that equation. right? Show that, prove that, that type of problem. Okay. Any other questions? You're all good with that. Okay. Example 3. Wait. What's the problem? Yeah? Which part? Sorry? First part. Yeah, so we're just doing the left-hand side. Okay, so dx by dt, that's on the left. So what is x? This is x. So we're doing the time derivative of that fraction. So that's the left-hand side. And then the right-hand side was alpha minus x squared. So we take the x there, alpha minus x squared, and we're checking that the two sides match. Okay. Yeah, so this is the left-hand side, dx by dt from that equation, and then the right-hand side, alpha minus x squared. So in both cases, x was the alpha squared t over alpha t plus 1. Okay, and we just substitute. Okay, any other questions? You're good. Okay, example 3. Okay, something from thermodynamics. Okay, Boyle's law for a gas. No, I'll wait for you to be done talking. That's fine. You want to carry on? Finish your conversation? No, you're done. Okay. Boyle's law for a gas is given by PV equals C, which is some constants. Okay, so you'll see quite a lot of this later on when you do thermodynamics in physics. So P, that's the pressure. V, that's the volume. And C, that's just some constants. Okay, so show that. The isothermal compressibility is given by beta. So we had that in the list of applications. So minus 1 over V dV by dP. And we want to show that this is equal to 1 over P. Again, P, that's the pressure. V, that's the volume. Okay, so how do we go about doing that? Well, we're given the equation here. Okay, PV equals some constant. And we want the dV by dP. So we want V prime. So let's start off with the equation that's given. So PV is some constant C. Okay, so this is an implicit equation, right? Like we had before. So we got P times V equals C. We don't have V as a function of P, right? It's all mixed together. So this is implicit. How do we get V prime? We take the derivative on both sides. So implicit differentiation, we're going to have d by dP of P times V is d by dP of C. Right, like we did before with the implicit functions. Okay, so we've got the derivative of a product. We have to do the product rule. So the derivative of P with respect to P, that's just going to be a 1. So there'll be 1 times V plus P. Okay, leave the first one alone. Derivative of the second, that's going to be dV by dP. And then the derivative of a constant, that's going to be 0. Okay, so we get P times dV by dP is minus V, just taking that over to the other side. Then we can divide through by P. So we get dV by dP is minus V over P. Okay, that's great. So we've got that part. This part over here, dV by dP. We know what that is. So let's substitute it in and see what we get. So beta is minus 1 over v dv by dp. We know what dv by dp is now, so we can substitute that. So this is going to be minus 1 over v. dv by dp was minus v over p from the working we had before. Minus and a minus, that makes a plus. V at the top, v at the bottom, that's going to cancel. So we get 1 over p, which is what we wanted. Any questions on this one? Scroll up, yep. To the question or the working?
The one thing.
The,
After we're taking the German on both sides.
yeah,
So up.
up, yep.
Okay, we get that part of the word thing equals costs.
Yes,
So the derivative on both sides.
d by dp on both sides, yeah.
Then the part below is my head.
Product rule. Okay, so product rule, that will be dp by dp times v plus p dv by dp. So that will be a 1 times v plus p dv by dp. But 1 times anything is just that thing, dv by dp, and that's what we have over there. Okay. Any other questions? No questions. Okay. Example 4. Let's do it. Yep, example 4. Okay. The dynamics of a system of x and y are given by dx by dt is equal to x1 minus y squared, and dy by dt, that is given by 2xy. Okay, so here this is just a very general type of problem. So dynamics of a system. Okay, so in practice, the system can really be anything. There's a few examples we'll look at. So it can be like populations. So you can have population X and population Y, okay, and they're changing. So like a system of people, you can call a population. So populations X and Y, okay, and then the rate of change of the number of X people is equal to that. The rate of change of the number of Y people is given by that, and they're related to each other by this equation. Or you can think of X being supply and Y being demand, right? Like from economics. So d by dt, that's the rate of change of supply that businesses will provide. dy by dt, that's the rate of change of demand. You know, that's what the consumers will buy. And there might be some equation for the two. Or you can have x being a position of particle 1, position of particle 1. Y is position of particle 2. Okay, and then dx by dt, that's the speed of particle 1. dy by dt, that's the speed of particle 2. And there's some equation describing the two. Okay, maybe there's some forces between them or something like that. Okay, but whatever the application is, in general, we have some equations, 2 of them, maybe 3 of them, that describe the dynamics. In dynamics, that is the rate of change. Okay, so whenever you hear dynamics, That is the rate of change of something. Okay, so the system is in equilibrium